Today we are going to explain our design, secure DNS caching using custom network processor, and also show you how we emulate the design and test and verify the functionality. So as we see, we are implementing it on a custom network processor. We are using the Xilinx Vertex 2 Pro platform for the design of our processor, and we are modifying the reference router design of the network processor of the net FPGA to include our processor in the design flow. And our processor's data memory has been replaced with a FIFO in which the packets come and sit, and our processor would process any packet and send it back. For our applications, we choose to process only DNS queries and cache DNS responses. And yeah. Moving ahead, I will like to show you the data lab platform we are going to use for network emulation. And we have already written an NS script and network simulator script and swapped an experiment. Here we have a net FPGA and 4 nodes. The net FPGA has a control node, which is a PC on which we run all the software related applications for the net FPGA. And we have 4 nodes here. For our application, we are going to use N0 as the client, which will request domain name resolution for the IPs of N2 and N3. And N1 would be the backend DNS server, which will be helping our net FPGA, which runs the secure DNS caching application. And if there is a cache miss, N1 would respond, and the net FPGA would cache the response before sending it back. And to add to it, we have added a feature of authentication based on RSA key exchange. And authentication for domain name resolution has been implemented here. And whenever N0 requests a DNS resolution for N3, N0 should be authenticated, and this authentication is established based on secure key exchange followed by symmetric key exchange between the nodes. And here the nodes involved are the net FPGA and N0. And once this symmetric key is exchanged, net FPGA updates that N0 has been authenticated, and further requests from N0 for N3 would be directly processed without any need for authentication. Also, DNS caching is performed at net FPGA, so the initial request for any node would be routed to N1, but further requests are taken care of by the net FPGA. And as we can see, the custom network processor, we have designed a custom processor, and this processor operates at 180 MHz frequency. It is a 4-threaded processor, and we have provided instruction support as well as compiler support for the processor. And let us move to the emulation platform. Here I have already logged into Data Lab and also NF06. As you can see here, I will just log out and log in for you just to show you what I'm trying to do here. And I have 2 nodes for NF06. This is the net FPGA nodes, and I have 2 windows for N0 and 2 windows for N1. Now initially we are interested in the NF host because we have to download our bit file, for which we have to reprogram the net FPGA, configure the Ethernet interfaces, and download the bit file. I have written a Perl script which will take care of all of these sequentially. And as you can see now on the screen, the net FPGA is being reprogrammed, after which the Ethernet interfaces will be configured, and the bit file would be downloaded, after which we are loading a set of data into the memory. This is just used to match it against the packet and identify whether it's a DNS query or a response, and only then act upon the packet. All other packets are just written into the FIFO and then read out of the FIFO without any modifications. And Yeah, once we are done configuring the netfpga, I will run another script, and this script would load the instructions into the instruction memory. And once the instructions are loaded, I will move to the second window. As I have already told you, we are using RSA key exchange for authentication, and I'm going to run the RSA server socket code on the netfpga, and the server would compute its n, e, and d. Here n and e are the public key, and d is the private key of the server. And the server will be waiting and listening for any request from a client initiating RSA key exchange. Once the client initiates the RSA key exchange, the server responds by sending its public key, and the client would then encrypt its public key as the message and send it to the server. And the server, upon receiving this message, just decrypts the message using its private key, and the server now has the public key of the client. And then server would encrypt the symmetric key and send it back to the client. Along with this encryption and sending the symmetric key, the server would also update a location in the memory saying that N0 has been authenticated, or this respective client has been authenticated, which in our case is N0. So I have already logged in to two of the terminals, PuTTY terminals with N0, and two of the PuTTY terminals with N1. And I'm going to take root access in N0 and N1. This is because I'm running a raw socket client, and a raw socket server. This and I would need to capture all the packets coming in to the node, and filter out the packet based on the port number from which the packet is coming. And I would also need to run a TCP dump on N0 and N1, so I'm going to use ifconfig to find out the Ethernet interface on which it has to be run. And as we can see, Ethernet 4 is using the IP 10.1.0.3, and I'm going to run TCP dump on Ethernet 4 interface, and I'm going to run a filter only for UDP packets. And the same will be repeated on N1 side, and the IP 10.1.1.3 is mapped to Ethernet 3. I'm going to run TCP dump on the Ethernet 3 interface. And I'm going to apply a similar filter for UDP packets. This is because we all know that the DNS queries are UDP packets. So as we have seen now, I have run TCP dump on both N0 and N1. Now I'm going to initiate the Python server code on N1. This will listen to incoming DNS queries and respond. And what you see here printing is the destination port of all the packets coming in. We are accepting all the packets, but we are looking for destination port for which only destination port 2328 for which at which DNS queries are forwarded from N0, and the DNS reply will be sent on port 251D. Now I have run the server here. I am going to run the client that generates the DNS request for N2 on N0, and as we can see, the request is going through and it is being cached. Now we would like to regenerate the request for N2, and this time the processor would respond, and the DNS response is seen here as 10.1.2.3, which is the IP for N2. Now if we generate a request for let's say N3, the request would go through, but it will also go through to the other end at N1, and the response will be cached by the server, but we will with the response from the NetFPGA would contain a message saying authentication is required, and this message coming back from N2, as we can see here, authentication required, initiates a client socket code on N0, and the client will generate its NEND, and it will receive the server's public key, and the server in turn will obtain a connection from the client, and he will receive the client's RSA key, and he will simultaneously update as well as send the symmetric key. He will also update the memory location saying that N0 has been authenticated. Now, since the previous request for N3 has been raised and it has not been processed and an authentication required message has been sent, the request would time out. So we have added a feature for waiting for 20 seconds, and the request would automatically time out and it will generate a new query, and this time the query will be processed by the server, and we are able to receive the response 10.1.3.3. and this is our secure implementation. We are authenticating before providing the DNS response, and we are also using the opportunity to cache before authentication. And the best part about this design is DNS server at the backend has also been authenticated with the key, and all the communication from the NetFPGA to the DNS server would be encrypted. And you can see that DNS query goes in, but the other message would be encrypted, and the query would be processed at the other end, and the message coming out would be encrypted, but when it comes to the node, that message will be decrypted, and the IP of that message, the IP in that message has been taken out, and we are able to identify that it is a DNS response, and identify the response coming from the node or the NetFPGA. And this level of security between the NetFPGA and the DNS cache is ensures that we are avoiding IP address spoofing for the DNS cache. Any faulty node or any Trojan which is operating as the DNS server at the backend might respond with a wrong IP address for the query, and we will not be able to resolve the request properly. But since we are encrypting the message with the symmetric key exchanged by RSA key exchange, only only N1 and the NetFPGA would know the symmetric key, and the communication between the two nodes is encrypted, and nobody can tamper with the packet. So that's all for today. Thanks folks for watching.